This $50 barrel holds 66,000 BTU of cooling. That is more than 5 ton-hours, enough to run a window air conditioner for 8 hours, and it will hold exactly the same capacity in the year 2055 that it holds today. No lithium, no cobalt, no degradation curve, no warranty that expires. Yet we are told that storing energy at home means $15,000 of batteries that lose capacity from the day you switch them on. This is called ICE thermal energy storage, and it is not fringe. Southern California Edison paid to install it across its territory. The Bank of America Tower in New York runs on it. The largest manufacturer in the field has been building these systems since the 1980s. By the end of this video, you will know the physics, the real numbers, the exact parts list with prices, and the one honest catch that decides whether this works on your street or not. I am going to give you that catch too, and I will give it to you with arithmetic rather than enthusiasm, because it is the number every other video on this subject leaves out. 2 quick clarifications before we start, so nobody feels misled. The barrel is $50. A complete working system with insulation, a coil, a pump, and a fan runs $200 to $400 if you already own a chest freezer. And this does not create cooling out of nothing. It moves cooling in time, from the cheap hours into the expensive ones. And by the end, you will see exactly what that is worth in dollars. Now let me show you what you are currently paying, because that is the whole reason this matters. Air conditioning is the single largest electrical load in an American home during summer, accounting for roughly 17% of residential electricity use nationally, and far more than that across the South and Southwest. Here is the trap. Your air conditioner works hardest at precisely the hour electricity costs the most. Utility peak demand in summer typically runs from about 4 to 9 in the evening. The sun has been loading heat into your walls all day. People arrive home, and solar generation falls off a cliff exactly when demand climbs, under time-of-use rates, now standard across large parts of the country. The gap between off-peak and on-peak pricing is commonly 2 to 4 times. So every summer afternoon, you buy the most electricity you will buy all day, at the highest price you will pay all day in the same 5-hour window. The conventional answer is a lithium battery bolted to your garage wall. A Tesla Powerwall 3 stores 13.5 kilowatt hours and lands somewhere around $15,000 installed. Tesla's own warranty guarantees 70% of original capacity after 10 years. That is not the failure case. 70% is the number the manufacturer is comfortable printing. Your solar panels carry a 25 to 30-year warranty. Across that lifespan, you are buying 2 to 3 battery replacements simply to keep using the energy your own roof produces. Every retired pack is classified as hazardous waste, in a country where fewer than 5% of lithium-ion batteries currently get recycled. And it is worth understanding what sits behind that $15,000 box before it reaches your wall. Lithium is extracted from open brine operations in the Atacama Desert in Chile and from hard rock mines in Western Australia. The brine process involves pumping mineral-rich water into vast evaporation ponds and waiting months for the sun to concentrate it in one of the driest inhabited places on Earth, where water is the scarcest resource there is. The refined material is then shipped across the Pacific to sell factories in China and South Korea, assembled into packs and shipped again to the United States. It arrives in your garage, works for a decade, and then becomes a hazardous waste problem somebody has to solve. That is the supply chain behind the storage solution you are told is the only one available. Now hold that next to a $50 barrel of tap water that never leaves your property and never needs replacing. Now the alternative, and it begins with a number most people have never encountered. The physics is called latent heat diffusion. It is the energy required to change a substance from solid to liquid without changing its temperature by a single degree. For water, that number is 334 kilojoules per kilogram. In American units, 144 BTU per pound. Compare those two figures directly. Raising 1 pound of water by 1 degree Fahrenheit takes 1 BTU. Melting 1 pound of ice at 32 degrees absorbs 144 BTU without the temperature moving at all. The phase change alone stores 144 times the energy of a 1 degree temperature swing. That is why ice in a glass keeps a drink cold instead of simply diluting it, and it is the entire foundation of this technology. Ice is not cold storage in the way people picture it. It is a battery, and the charge is held in the transition between solid and liquid. Now, the arithmetic on the barrel. A standard 55-gallon drum holds about 208 liters, which is 208 kilograms of water. Multiply by 334 kilojoules per kilogram, and you get roughly 69,000 kilojoules. Convert that, and you have about 19.3 kilowatt-hours of thermal energy, or approximately 66,000 BTU. 1 ton of air conditioning is 12,000 BTU per hour, so that single drum holds 5.5 ton-hours of cooling. A typical window unit is rated at 8,000 BTU per hour, which gives you roughly 8 hours of equivalent output from one barrel, and the storage medium is water. It costs nothing, it never degrades, it cannot catch fire, it has no cycle limit, and no calendar life. Here is the second number that explains why engineers choose ice over chilled water. Storing energy as sensible heat, meaning cold water rather than ice, is far weaker. Chilling a pound of water through a 20-degree swing stores 20 BTU, freezing that same pound stores 144. Roughly 7 times the storage in the same tank. That is why every serious commercial installation freezes. Now let me prove this is not theoretical, and I am going to do it at 3 separate scales. Start with utility scale. In 2014, Southern California Edison contracted with a company called Ice Energy for over 25 megawatts of distributed thermal storage capacity. The product is called the Ice Bear. It bolts onto an existing commercial air conditioning system, freezes water overnight, and delivers roughly 6 hours of cooling the following day. Read that again. An American utility spent money installing ice tanks on other people's buildings specifically to pull demand out of the afternoon peak. The reason is structural. An electrical grid must be sized for its worst hour of the year, not its average. Peaking plants sit idle most of the year and are among the most expensive and least efficient generators on the network. Fired up because everybody's air conditioning switched on at once. Moving a kilowatt out of that window is worth far more to a utility than saving a kilowatt at midnight. In many cases, it is genuinely cheaper for them to fund storage on your property than to build another plant. Now, commercial scale. The established manufacturer in this field is Kelmac, founded in 1947, building ice thermal storage since the 1980s, and acquired by Trane Technologies in 2018. Their tanks sit in thousands of commercial buildings across North America. One Bryant Park in Manhattan, the Bank of America Tower, operates a large ice storage plant using dozens of tanks to shift its cooling load out of peak hours. That is a flagship skyscraper in the most expensive real estate market in America, running on frozen water. Baltimore Aircoil builds competing systems. ASHRAE, the professional body that writes the standards American HVAC engineers design to, publishes design guidance for thermal energy storage. This is not an alternative technology. It is mainstream commercial engineering that simply never came home. And there is a fourth group already doing this quietly that nobody writes articles about. Walk into almost any small commercial kitchen, brewery, dairy, or florist, and you will find a version of this running. Restaurants build ice overnight to hold walk-in temperatures. Small dairies use ice banks to crash cool milk the moment it comes out of the animal. Craft brewers build glycol reservoirs and freeze them off-peak to hold fermentation temperature through the following day. None of those people call it thermal energy storage. They call it an ice bank. And it has been standard equipment in food businesses for generations because the arithmetic was always obvious to anyone paying a commercial electricity bill. So the technology never actually disappeared. It stayed exactly where the electricity bill was large enough for somebody to do the sums, and it never crossed the line into ordinary houses, where nobody was told there was a sum to do. Now, a historical scale, and this is where it gets genuinely remarkable. In Persia, around 400 BC, engineers built domed mud brick structures called yakshol, with walls several feet thick, designed to make and store ice through a desert summer. Water was run into shallow shaded channels at night, froze in the cold desert air, and was moved into the insulated chamber below. Ice, in one of the hottest places on Earth, with no machinery at all, 2,400 years ago. Then Boston, 1806. A merchant named Frederick Tudor loaded a ship with ice cut from New England ponds and sailed it to Martinique in the Caribbean, betting that people in the tropics would pay for something they had never had, The first voyage lost money, and he was ridiculed for years. He persisted, worked out that sawdust from local sawmills made superb cheap insulation, built insulated ice houses at the destinations, and turned it into one of the great American export industries. By the 1840s, New England ice was reaching England, the Caribbean, and Calcutta, arriving after months at sea with a substantial share still frozen. At its peak, the trade employed tens of thousands of people. Blocks were cut from frozen lakes with horse-drawn saws every winter, packed into enormous ice houses holding tens of thousands of tons, and delivered by wagon through the following summer. Nearly every American town had an ice house and a delivery route, and nearly every kitchen had an insulated wooden cabinet called an icebox, an entire national cooling system running on cold weather and sawdust. It collapsed in the 1920s and 30s, not because ice stopped working, but because a machine in your kitchen that made cold on demand beat a man delivering a block twice a week. Within about 2 decades, all of it vanished. The ice houses were demolished, the trade disappeared, and the generation that grew up with an icebox simply stopped mentioning it. Proven at utility scale by Southern California Edison, proven at commercial scale in Manhattan skyscrapers, proven at national scale for a century before refrigerators existed. So why can you not walk into a hardware store and buy a residential ice storage unit? The barrier is not physics, it is paperwork. The Inflation Reduction Act of 2022 created a 30% federal tax credit for residential clean energy, and standalone battery storage of 3 kilowatt-hours or larger qualifies directly. Thermal storage sits in a far murkier position in residential guidance. No manufacturer produces a certified, listed residential ice storage product for a homeowner to buy. There is no installer network trained on it, no permitting pathway in most municipalities, and no line in the appraisal guidelines that recognizes it as an improvement. A homeowner who installs a lithium battery gets a federal credit, a turnkey installation, a manufacturer warranty, an insurance rider, and added appraised value. A homeowner who builds an ice storage system in their garage gets none of those things, no matter how well it works. The market was never designed to exclude thermal storage. It was designed around batteries, and anything outside that shape is invisible. In a market where credits and certifications decide what gets built, invisible produces the same result as prohibited. If working out the honest numbers for your own home is the part you actually want, the full worked calculations, the sizing tables, and the parts lists are linked below. Everything in this video with the arithmetic shown rather than asserted. Now let me show you how to build one. The storage vessel is the simplest component. A food-grade 55-gallon HDPE drum runs $20 to $60 used from a food distributor or a car wash supply. A steel drum costs about the same. In practice, several smaller sealed containers often beat one large drum. Water expands roughly 9% when it freezes, so smaller vessels with proper headspace are far easier to manage. And more surface area means faster freezing and faster heat transfer coming back out. Many working builds use a bank of sealed jugs inside an insulated box. Insulation is where most homemade systems fail, and it is not optional. 2 inches of rigid foam board is the minimum, and 4 inches is substantially better. Owens Corning Foamular, or the equivalent, runs $30 to $80 for what you will need, at roughly R5 per inch. Pay particular attention to the lid and the base. Heat rises, so an uninsulated top loses more than any wall, and a drum standing directly on a concrete slab is in permanent thermal contact with the ground. Put foam underneath, seal every joint with foil tape, and treat each gap as a hole in a bucket. A properly insulated store holds most of its ice for 2 to 3 days with no input at all. If yours melts out in 12 hours, the fault is insulation, not physics. The heat exchanger is how you get the cooling back out, and there are 2 approaches. The air version is simpler. Build an insulated box around the ice, run a small fan through it, and duct the chilled air into the room. A quiet, inline duct fan runs $25 to $50. The liquid version performs better. Run a coil of half-inch copper, or PEX, through the ice. Circulate water or glycol with a small pump, and pass that loop through a radiator with a fan on it. A 12-volt circulation pump runs $20 to $40. 50 feet of PEX runs $20 to $30, And a used automotive heater core makes an excellent radiator for $30 to $60. For controls, an Intermatic mechanical timer at $15 to $30 is enough to run your freezer only during off-peak hours. And that timer is doing most of the financial work in this entire system. Total build cost, excluding the freezer, lands between $200 and $400. The operating routine is simple enough to forget about once it is set. Your timer switches the freezer on when your off-peak rate begins, usually somewhere around 9 or 10 at night, and switches it off before the peak window opens in the afternoon. Your pump and fan run only during the peak, pulling cooling out of the ice exactly when grid power costs the most. A cheap plug-in energy meter, around $15 to $20, tells you precisely what the freezer is consuming, and a $5 thermometer in the store tells you how much ice you have left. That is the whole system. 2 switches on a schedule, and a routine that repeats every day of the cooling season without you touching it. Build it once in a weekend with basic hand tools. No electrician, no permits for a plug-in system, no specialist training. Now the catch I promised you at the start, and this is the number every other video on this subject skips. The barrel is not your constraint. Your freezer is. A standard chest freezer removes heat at roughly 300 to 500 watts thermal when running. Over 10 overnight hours, that is 3 to 5 kilowatt hours of heat removal, which will freeze approximately 40 to 50 kilograms of water. 40 kilograms is around 10 gallons, not 55. That gives you roughly 13,000 BTU per night, or about 1.5 hours of window air conditioner output. So a full barrel is not an overnight charge. It is a multi-day store. That single fact reshapes how you should design this. And there are 3 sensible responses. Response 1, right-size it. Build for what your freezer can genuinely make in a night, meaning 10 to 15 gallons of ice, and use it to cover the sharpest 90 minutes of the afternoon peak rather than the whole day. Response 2, extend the charging window. Run the freezer through the whole off-peak period rather than only overnight. 20 hours of charging at 400 watts gives you roughly 8 kilowatt hours of ice, which is around 27,000 BTU, or 3.5 hours of cooling. Response 3, add capacity. A second chest freezer, or a used commercial ice machine, doubles your charge rate. Freezers are the cheap part of this system, and they turn up constantly on second-hand marketplaces. I would rather give you that arithmetic and have you build something that works than sell you a fantasy about a barrel that fills itself overnight. So what is it actually worth in dollars? Take the realistic version. You shift 3 kilowatt hours of air conditioning consumption per day out of the peak window. If your utility charges roughly 30 cents on peak and 10 cents off peak, that 20-cent differential across 3 kilowatt hours is 60 cents a day. Across a 100-day cooling season, that is $60. Add the efficiency gain from running refrigeration into 70-degree night air instead of 95-degree afternoon air, which is genuinely worth another 10 to 15%. And you are somewhere around $70 to $90 a season. A $300 build pays for itself in 3 to 4 summers, and then keeps paying for the next 25. That is a real return, and it is not the return of a miracle. Anybody promising you thousands of dollars a year from a barrel of water is selling something. There is a second condition, and it decides everything. This only pays if your utility charges you differently at different hours. If you are on a flat rate, where a kilowatt hour costs the same at 5 in the afternoon as it does at 2 in the morning, then shifting your consumption earns you almost nothing beyond the small efficiency gain from cooler night air. So before you buy a single component, open your electricity bill and look for the words time of use, or peak and off-peak, or on-peak pricing. If those words appear, this project has a real financial case on your street. If your bill shows one flat number, the case is far weaker, and I would rather you knew that before spending $300. Time of use rates are spreading rapidly and are already default in several states, so it is also worth checking what your utility is planning, since a system built this summer may be worth considerably more next year. Now the honest limitations, all of them. Round-trip efficiency for a well-built home system runs roughly 70 to 85%. A poorly insulated one does considerably worse. Capacity is modest. One barrel covers one room, not a house through a heat wave. Space is the axis where lithium wins outright. A battery holding comparable useful energy is dramatically smaller than a drum of ice. This stores cooling only. It will not run your lights, your refrigerator, or your Wi-Fi, and it does not make you off-grid. Humidity matters more than most people expect. In a dry climate, the cold air coming off the coil feels excellent. In Florida, in August, that same coil pulls water out of the air constantly, which consumes part of your stored energy on dehumidification and demands proper drainage. And charging is slow, which makes this a predictable daily routine rather than an emergency system. The safety picture, by contrast, is the easiest in this entire field. There is no pressure vessel, no combustion, no toxic chemistry, and no fire risk. The worst-case failure of a barrel of ice is a wet floor. The genuine cautions are electrical and biological. Any pump, fan, or freezer near water goes on a ground fault circuit interrupter, and that is not a suggestion. Leave headspace in every sealed container. Since water expands about 9% freezing and a completely full vessel will split, keep the system clean and drained. Standing water in a warm, dark box grows mold, and you do not want a fan blowing that into your living room. If you use glycol in a closed loop, use propylene glycol rather than ethylene glycol. The former is the food-safe variety, and the latter is toxic. And if you run a chest freezer on a timer, do not store food in it. An appliance that cycles off for hours is not a food storage device. Here is a claim worth checking, and I would genuinely like you to check it. Southern California Edison, one of the largest utilities in the United States, contracted for over 25 megawatts of distributed ice storage in 2014. Search the company name Ice Energy alongside Southern California Edison and read the filings yourself. No lithium battery on the market in that year could have been deployed at that capacity for anything close to that cost, which is precisely why a utility chose frozen water instead. There is one more thing worth sitting with before you go. Nobody suppressed this. There is no buried patent, no destroyed research, and no conspiracy to find. What happened is far more ordinary. A technology that required a routine was replaced by one that required nothing. And within 2 generations, the routine was forgotten so completely that the physics behind it now sounds like a discovery. Your great-grandmother knew that ice held cold. She had a cabinet in her kitchen built around that single fact, and she planned her week around a delivery. We built machines that removed the need to know it, which was genuine progress. And the knowledge went with the inconvenience. The interesting question is not why we stopped, it is how many other things we quietly stopped knowing in exactly the same way, in exchange for something that plugged in. So here's my question. If you had one garage, one summer, and $300, would you put it into a barrel of ice that shifts your air conditioning off the afternoon peak and still works in 30 years? Or would you save toward a lithium battery that does more jobs and needs replacing twice in the same period? Drop your answer in the comments. And tell me what your utility charges at 5 in the afternoon compared to 2 in the morning. That single number decides whether this makes sense on your street, and I read every one. Next time I am going to show you the sand-filled tank that stores heat for months at a time, holding it through an entire winter with no chemistry and no moving parts, and why a small Finnish town built a commercial one and connected it to their district heating network. Subscribe so you do not miss it, and remember that the technologies we abandoned were almost never beaten on performance. They were beaten on convenience.